Very happy to introduce Ron Weiss, who did his PhD work right here, three floors up, in Lab Rosa, which was research recognition of speech and audio. Okay, it was Dan Ellis's group. He had funny names for things.
I'm going to continue.
And then he did a post. Hello. Postdoc at NYU. Followed by his brilliant career at Google. Now for almost 10 years, I guess. 9 years. Which is almost 10. With that, let me hand it over to Ron.
Thank you, John. Thanks everyone for sticking around through such a long day. Thanks also to the previous speakers for hopefully making it easy for me to jump through most of this introductory material quickly. I'm sorry for being tall. All right, so I'm going to talk about generating speech from speech and pushing end-to-end models way too far. You can be the judge, I guess. This is joint work with Fadi Biazzi, who's sitting over here in the audience, is going to come give a live demo at the end, hopefully, if we have time. Jia, and lots of other people in lots of different parts of Google. So I'm just going to jump right in. So I'm going to talk again about these end-to-end trained models. And the idea, again, is we want to basically throw away all the complicated big systems that we've been building for 30, 40 years. Okay, I will try. And replace them with single neural networks. All right. Why it's simpler, sort of less complicated training data to deal with. For example, we don't have to care about phonemes and pronunciations or things like that. Simpler implementation. Generally, the models are smaller, which is nice if you want to deploy them on a phone, which we will do. They might have lower latency inference and so on and so forth. The other sort of nice thing is by sort of directly optimizing for the target you care about, if you're lucky, will sort of naturally avoid compounding errors that you get when you sort of glue together lots of different systems. And also, it might be that there's some features in the input that are actually useful for generating the output that a conventional system might unintentionally discard. And we're going to see some of that with sort of prosody being maintained through some of these systems. As sort of an outline, I'm going to take you through a journey that myself and several of my colleagues sort of have gone through over the past 2 or 3 years in trying to build ever more complicated end-to-end models for difficult speech tasks. So we're going to start by talking about speech-to-text translation, so something that looks like speech recognition, except we're going to go, in this example, from Spanish speech to English text. Then, as the last speaker introduced, I'm going to talk about this model we call Paratron, which goes directly from speech to speech for voice conversion, and actually I'll show how you can use it for speech separation and a little bit of a toy task. And finally, we're going to kind of combine those two ideas together, Paratron and translation, into a model that can do direct speech-to-speech translation. So we're not very creative. We call this one Translatitron. Please do come give me a better name. All right. So just as sort of building blocks, everything here is going to be a sequence-to-sequence network with attention, and we're going to build off of sort of two existing approaches in the literature. One is this family of models for speech recognition, the most catchy named of which was called Listen, Attend, and Spell. And again, just as a very quick review, you've got sort of three components: an encoder network, which takes audio features and generates some latent representation; a decoder network, which generates transcripts sort of one character at a time in an autoregressive way; and then this attention mechanism in the middle, which just sort of aligns the two. So it's a pretty powerful model, as you'll see. The other building block is, this is the source of all the names, the sequence-to-sequence network for text-to-speech synthesis, which we called Tacotron. And it's basically the exact same idea, except sort of the directions are reversed. Here at the input, you've got some representation of text, characters that get encoded, then go through attention, and then a decoder network which generates spectrogram frames. And again, this is an autoregressive decoder, one frame at a time, and it just gives you a spectrogram. If you want to get audio from that, you can pass the output through some kind of vocoder neural network. I'm not going to focus on that too much here, but WaveNet, WaveRNN, WaveGlow, any of these things work. Okay, so with that out of the way, let's dive in and talk about speech-to-text translation. So this is work that I did with several of my colleagues at Google Brain that published at Interspeech 2 years ago, and the title tells you everything you need to know. Mostly, sequence-to-sequence models can directly translate speech. How? Well, it's actually pretty straightforward, actually. All we did here was we took a speech recognition model and we changed the training data. So we throw away the transcript and replace it with a translation, assuming we have a large enough corpus of matching speech and translated transcripts. You can train this thing. We use the deeper listen, attend, spell architecture that Yu Zhang and company published in 2017. And so this is, again, we were not the first to try this. There was earlier work called Listen and Translate, better name than I had, sorry, which showed that this would work on a sort of relatively small corpus of synthetic speech. And so what we did in this work was basically scale it up a little bit and make it work on real speech. And so for training data, we used this Fisher Spanish to English speech translation corpus, which basically just takes the Fisher conversational Spanish speech recognition corpus, and then this group, Matt Post and folks at Johns Hopkins, went and crowdsourced English translations for the Spanish transcripts. So that gave us exactly what we needed to try this idea. And so the training set here, it's about 160 hours, so small to medium sized, maybe, by speech standards. And that's what we're going to train on and see if it works. And so we're going to compare 3 approaches. One is, again, just this end-to-end speech translation model. Again, it's a speech recognizer where we give it harder transcripts. That's it. And we're going to compare that to a multitask approach where we basically train 2 sequence-to-sequence models simultaneously, one to do Spanish speech recognition and another one to do the Spanish to English speech translation. And the idea here is we're just going to use the same encoder between these 2 networks. And so the hope is that sort of multitask training this thing will help regularize the encoder a little bit to learn a more useful representation, which might make it easier for the model to generate the correct transcript. Important to note that this, can you guys see my mouse? You can, okay. So this ASR decoder is only there for training. We don't care at all. We throw it away before we do inference. It's only there to sort of help improve the training. And so when we're doing translation, we just still take the speech and directly predict the English transcript. And finally, as a baseline, we create a fairly naive cascade of 2 separate sequence-to-sequence models. We just train on the original Fisher Spanish data speech recognizer. It's again listen, attend, and spell, but solving the easier task. And we also train on the same corpus. We train on the same pairs of English and Spanish text, I should say. We train a text neural machine translation model that goes from Spanish text to English text. And then during inference, we kind of do the dumbest thing you can, which is just run the recognizer, take the top hypothesis found during beam search, and then pass that through the translation model, and that will give us our English transcript, our English translation. So how does this work? Pretty well. So I guess I'm the first person to talk about translation today. So the metric that is used in that community is this thing called BLUE score. It's just a precision metric. Higher is better, unlike word error rate. The details don't really matter. And so, yeah, higher is better. And comparing these 3 approaches, we basically find that they all work just about the same. So this end-to-end speech translation works pretty well. Multitask training does indeed slightly help improve performance above it. And both of those are a little bit better than our simple cascade baseline, although I wouldn't read too much into that. But the point is, yeah, given sufficient training data, you can make this work, no problem. All right, this was the easy task. Let's try and make it a little harder. And so we followed up that work presented at ICASP this year at sort of a larger scale version. This one is led by Ye Jia and Melvin Johnson, and a whole other cast of characters, which we'll repeat. And so, yeah, what do? Here we're going to basically try to solve the same task on a larger training corpus. So what we did here is we collected this training set, which I call ST1, which contains 1 million utterances for speech translation. This time we're going in the opposite direction. We're going from English speech to Spanish text. And we're going to do that because we want to sort of build the best baseline we can. And we have better English speech recognition training data than we have Spanish. And so, yeah, it's about 1,000 hours of training data. So it's not quite an order of magnitude larger than the previous task. And again, we're just going to try the same thing, train a speech recognition model with translation targets. And again, we're going to compare this to another baseline cascade, except this time we're really sort of going industrial strength, if you want. So we're going to train an English speech recognizer on this huge corpus of about 29 million transcribed English utterances. So these are anonymized voice search logs that Google uses to train some speech systems. It's about 40,000 hours or so. So very big. And so it does a pretty good job. And we're also going to build a large-scale English text to Spanish speech machine translation model on this corpus of 70 million text pairs. So this is actually a superset of the ST1 data set, which we're going to use to train the direct model. All right. How do these things work? Well, first of all, it's a bigger data set, so we want a bigger model. It's about roughly a linear increase in the number of parameters compared, it's proportional to the increase in the data set size. So it's about 62 million parameters. And we find if you just train this thing directly on the small subset of 1 million examples, it does pretty well, actually. So you get a blue score of 49, which is quite good, although it's red speech, so it's maybe a little bit on the easy side. But it does not perform as well as this cascade. Of course, that cascade was trained on about 100 times more training examples, so it's not really the most fair of comparisons. So what we did in this work is we actually looked at a few different strategies for kind of trying to figure out how to shoehorn all of that speech recognition and machine translation training data into this speech-to-text translation model. And so the first approach, which worked pretty well actually, is to essentially pre-train. So what we do is we take our speech-to-text translation model, and at initialization, we basically copy the encoder parameters from the speech recognizer and copy the decoder parameters from the decoder of the machine translation system. That gives us an initialization that has seen 100 million examples. And we train from there only on the ST1 subset. And so that bridges most of the gap. We get up to about 54 points. We can do better, though. And the other approach that actually totally eliminates the gap is multitask training. Except here we've got sort of different training corpora for the different tasks, unlike in the original example. And essentially all we're going to do is we're going to train simultaneously the speech recognizer, the speech-to-text translation model, and the machine translation model. Just sharing encoders between the speech translation and ASR, and decoders between the speech translation and MT. So if you do that, again, this bridges the gap, and we can do as well as the naive cascade. So if you want to build a high-quality speech-to-text translation model, you can maybe take advantage of speech recognition and text-to-text machine translation training data. So this is encouraging. A little too encouraging. So I think the next thing I tried was to go all the way and see if we can train a model that goes directly from speech in one language to speech in another. Doesn't work. So again, we're just going to treat these big neural networks as building blocks and design a new network which just takes the encoder from the speech recognition or translation models and the decoder from a Paratron 2 TTS system and say, you know, the input is a spectrogram, the output is a spectrogram. Surely this will work. The only problem is we don't have training data. And so what we did is we cheated a little bit. We took the Fisher Spanish to English speech-to-text translation set, and we took a speech synthesis model and basically synthesized target speech for that corresponding to the English transcripts, and we're going to use that as our training data. So really, this is a slightly easier version, if you want, of the speech-to-speech translation setup, where we're going from speech in the voice of an arbitrary person to synthetic speech in a different language. Just to give you a sense as to what that sounds like, I'll play a quick example. Hopefully I will not make you go deaf in the process.
Yo soy Guillermo. ¿Cómo estás?
Sorry about that. Let's try that one more time.
¿Qué tal? Yo soy Guillermo. ¿Cómo estás?
That's the input, and the target output sounds like this.
How's it going? Hey, this is Guillermo. How are you?
So we want to make everything sound like the Google Assistant voice, which you're going to be hearing a lot of, so get used to it. Anyway, so we tried to train this thing on this 160 hours or so of training data. It doesn't work at all. Essentially what you get is a decoder that's pretty good at generating short strings of coherent spectrogram frames that are not at all related to the input. So, you know, it says things like this.
No nosebleed for New York.
I don't know where it hallucinated New York. This is what it should have said.
But I didn't have the money to stay very long.
Yeah, I'm not going to pretend that did some kind of smart semantic interpretation. But anyway, that does not work. But if we integrated multitask training, maybe that'll help a little bit more. So the idea here is, like we tried in the previous approaches, we're just going to try and simultaneously train a speech-to-speech translation model along with a speech-to-text translation model, sharing an encoder. And this kind of works a little bit. It starts to pick up attention and sort of occasionally output the correct transcript, but it doesn't work, the correct content. It doesn't work that well. I'll give you one example where it nails it. Oh, wow. That's HDMI for you.
Yes.
It got that one perfectly right. But, you know, most of the time it doesn't work very well. So here's a other one.
Tell her he used it, something like that.
So it got a few words that are actually correct at the end.
Sure, I think it's for constructing buildings or something like that.
Indeed, it was something like that, but not very close. Okay, so clearly we've bitten off a little bit more than we can chew here. And so I want to put a pin in this and sort of go back to this easier task of voice conversion. And again, this is a model that we called Paratron. It's actually Fadi's fault that we called it Paratron. Yeah, and this was just presented at Interspeech, I guess, a month and a half ago or so. Again, joint work with, or this was actually led by Fadi and myself and some other colleagues in speech and Google AI perception. All right. So we're going to start with this sort of hokey task, which we call voice normalization. And the idea here is we want to train a model that can take speech from an arbitrary speaker. Maybe they have an accent, maybe there's background noise, maybe they're not articulating well, whatever it is, and turn that into corresponding speech in the voice of a single sort of canonical target speaker. You can see where I'm going with this. But You can think of this as a text-independent many-to-one voice conversion system, if you want. But we're going to use the sequence-sequence network, so we need lots and lots of training data, and we don't have it. So we're going to synthesize it. Again, we call this network Paratron. It's the exact same architecture that we tried before for the speech-to-text translation, except now it's a slightly easier task. Multitask training still works, and all of the above. This time we're going to train on this giant corpus of ASR training data, and again, we're going to use the same parallel wavenet single-speaker TTS system to synthesize target speech. So this will take speech from anybody and make it sound like the Google Assistant. If anybody's familiar with Kurt Vonnegut, this is the Harrison Bergeron of voice conversion systems. Sorry, middle school joke. All right, so here's an example. Input.
How do you find the youngsters?
And target output.
How do you find the youngsters?
Again, get used to this voice. This works. It picks up attention right away, and it's trainable. It's great. So we compared a few different variations of this model. We evaluate things just by sort of seeing how well it maintains the semantic content. So we just basically take a pre-trained speech recognizer, run it on the output, measure word error rate. That gives us a quick and easy way to compare different models. And basically we find that without multitask training, it doesn't work super well. But if we do use that auxiliary decoder to predict the transcript of that speech, that sort of improves the word error rate by a third or so. And it turns out you can actually do slightly better if you train that auxiliary decoder to predict the phonemes corresponding to that speech instead of the graphemes. So like, who cares how you spell things as long as you get the sounds right is sort of the intuition there. And so once we put all this together, we get something that works pretty well. I've got some example inputs and outputs. Here's an input.
Please call Stella.
And the system indeed gets that.
Please call Stella.
Not too bad. Doesn't always get it right, though.
Please call Stella.
So different accent if you want. Actually, this is an accent that is different from the training set. The training data is all U.S. English speech, so you might be able to use that as an excuse to explain why this doesn't work so well. Here's the output.
Please call Stella.
So it should have been call.
Please call Stella.
Instead, Stella is cool. And so this model is actually kind of a lot of fun to play with because it just tries to project any speech-like sound you give it into TTS English. So here's an example in Spanish, I believe.
Música de Toña la Negra.
Let me play that again.
Pon música de Toña la Negra.
And so this is what Paratron thinks that should sound like.
Pom musica Latonia Lanera.
So yeah, at the end, Fadi's going to come and demo some more creative, maybe, examples. Or if you want to come hassle either one of us when we're going out for a beer, you can play with it on either of our phones and try and break it. All right, so that's Paratron. It's sort of a silly model. It's there maybe are some applications if you want to do work like some privacy potential applications if you want to anonymize speech or something like that, but it's not sort of obviously immediately useful for anything super important. So we thought we'd try a more interesting and useful task, which we call atypical speech conversion. So the idea here is we actually want to target users for whom their speech is sort of not so easily understood, both by people or by off-the-shelf speech systems. So, for example, users with dysarthria, or we didn't try it, but users who've had a laryngectomy or something like that, as we heard about in the last talk. And so, actually, specifically, we're going to start with a case study of speech from a deaf speaker. So, this is one of our colleagues at Google, who many of you might know, actually, and he was able to hear at birth, but he lost his hearing sort of at a very young age. So, he does not know how to speak. He's not able to speak and sort of as fluently as we can. And also importantly, he was born in Russia, and so he learned to speak Russian. and then, many years later, learned to speak English, sort of projected through his knowledge of Russian. So, it's a little bit. If you know Dmitry, you can understand him. But here's an example of what he sounds like.
I speech research scientist at Google. Before Google, I worked at IBM.
So what we're going to do basically is try and build a version of Paratron that can make him sound like the Google Assistant. Again, this is, you need parallel training data, at least for naive application of these approaches, and this is what we tried. So Dmitry is indeed a speech scientist and is very patient. And so he went and recorded about 13 hours of speech. You don't actually need 13 hours to make this work, but the more the better, obviously. And what we're going to do is take the normalization model that I described before, and we're just going to fine-tune it on speech from Dmitry. And hopefully that will lead to a model that works pretty well. I do want to note that the normalization model trained on 40,000 hours of real speech does not work at all on this sort of very atypical kinds of inputs. So here's an example input from Dmitry.
Information about Oklahoma.
Sorry if that's too loud. And this is what the model would output. The model before fine-tuning would output. Yeah, I don't know what that was saying either. Did I play the wrong one? It doesn't really matter. It doesn't get this right either. It got Homa. But after we do this adaptation, it works just fine. We used a different Google Assistant voice here just because we didn't want to change genders.
Here is some information about Oklahoma.
So you might have to take my word for it, but that is what Dmitry was saying.
Information about Oklahoma.
Another quick example. Again, I played this before, but I'll play it again. I don't know what that is supposed to be, but this is...
You can use your regular name outside the game.
Indeed, that is correct. So again, we sort of evaluated how well the system worked. We measured word error rates. We also did listening tests to measure, to rate the naturalness of the speech, and we find that it helps quite a lot. So the word error rate of the speech recognizer on Dmitry's real speech is almost 90%. After you adapt a Paratron model, it goes down to about 32. Paratron without adaptation makes it worse. So it seems useful. Okay, and so, yeah, the other, here's another nice demo where Dmitry is using Fadi's demo on a phone sort of as an intermediary between him and a Google Home Assistant device. So let's see how it works. What?
That the show was from Stagnant Valley.
Southern University and A&M College is 645 miles away from Missouri.
What is the definition of rain?
Here's the definition of rain. Moisture condensed from the atmosphere that falls visibly in separate drops.
What is the definition of rhythm?
Hey Google, what is definition of rhythm?
Here's the definition of rhythm. A strong, regular, repeated pattern of movement or sound.
Yeah, so in case you didn't believe that Dmitry is deaf, he didn't even realize it worked until the other phone on the table showed him that it was recognized correctly. Yeah, so this is sort of immediately useful, actually, for someone like him. And we've played with the same approach for different users. I think there's some demos online of someone with muscular dystrophy for whom this approach works, and we're also working with some ALS patients and some other kinds of severe atypical speech cases. So, yeah, this is actually useful. And just sort of as another quick note, everything we've been trying to synthesize so far is this silly TTS voice. Again, sometimes it's useful, but it still seems a little bit limited. So just as a indication that this approach would work on other speech tasks, we trained this on a sort of a speech separation by synthesis task. We train this model on instantaneous mixtures of up to 8 overlapping speakers. It's sort of a moderate average SNR of about 12 dB, and just trained to reconstruct the speech from the loudest speaker in that mixture. And so, this works too. And importantly, you can train this model to generate speech from arbitrary speakers. It doesn't only work on a Google Assistant voice. Here's a quick example.
Both managements are very supportive.
Gets that right.
Both managements are very supportive.
So, I wouldn't necessarily suggest that this is a good speech separation system on its own. Certainly it's not going to do well in terms of any waveform reconstruction metrics like, SDR or whatever. But it might be a useful component in something masking-based one day. Just a proof of concept. All right. So that worked so well that we thought we'd try again on this speech-to-speech translation. And this was also actually presented at Interspeech this year. Again, joint work with the same cast of characters that we've seen before. So let's see what we did. Essentially we just applied the lessons we learned from scaling up the speech-to-text translation model and Paratron. Again, we're going to work on this Fisher Spanish to TTS English data set, at least to start. And basically what we needed to make this work is basically use a much bigger model. So this is about, I don't remember the exact number of layers in Paratron. The details are in the papers, but it's about twice as many parameters. We use multi-head attention like we did in the speech-to-text translation. And multitask training, again, is quite important. And actually what we do here is sort of, we train 3 tasks at once. We find it useful to predict both the phonemic transcript of the input speech and the phonemes corresponding to the target output speech. Both of those together sort of help. And like Paratron, we're predicting phonemes instead of graphemes because we don't want to distract the network and have it try and figure out English or Spanish orthography rules or anything like that. There are a few other tricks to pick up attention. I'm not going to bore you guys with the details because beer awaits. But let's listen to some examples. So this is the example we heard at the beginning. Let's play it again.
¿Qué tal? Yo soy Guillermo. ¿Cómo estás?
And this is the target output.
How's it going? Hey, this is Guillermo. How are you?
Doesn't sound like Guillermo to me. This is what Translatotron says.
Hi, I'm Guillermo. How are you?
Not too bad. This is the output of a speech recognizer, so don't read too much into the transcription errors. And if we compare this again to a sort of naive baseline where we just take the speech-to-text translation model from way back at the beginning of the talk and pass the output through a Tacotron 2 TTS, this is what we get.
Hey, I'm William. How are you?
Let me play that one more time.
Hi, hey, I'm William. How are you?
So a few interesting observations. Number one is the prosody is kind of crazy. It turned Ketal to haye instead of reconstructing the disfluency somehow, which Translatotron did. Also, for whatever reason, it decided to translate Guillermo to William, which is the correct translation. But generally, that's not what you want when you're building a system like this. Someone's name is their name. You don't have to project it into the target language. But, it's clearly working to some extent. Well, Translatotron is actually clearly working pretty well in this example. How am I doing on time? I'm not going to play the audio for this, just so we have more time for a demo. But here's an example where Translatotron does sort of crazy things. The input speech includes this phrase, los pasajes. Apologies for my terrible Spanish. the correct translation of which is the tickets, but Translatotron actually translates that kind of to the corresponding cognate, maybe, as the passage, which is sort of a weird error mode. And yeah, there's actually another example of this. Passar in this utterance gets translated to pass. I forget what the correct translation is there. It's probably, yeah, it's like happen. Anyway, it's not always perfect. So we did some quantitative evaluations. Again, it's kind of hard to directly assess the quality here, so just as a crude metric of translation quality, what we did is we took the output speech from all these systems, transcribed it using a pre-trained LibreSpeech recognizer, and then we just computed the blue score on the output. So, you know, as we saw before with Guillermo, which I guess probably doesn't appear anywhere in the LibreSpeech training set, the recognizer makes mistakes, and so you can sort of think of this metric as a lower bound on how well these models are doing. And so just comparing the different approaches, again, without multitask training, this does not work at all. I'm kind of impressed that it even got a blue score of 0.6 on the test set, probably just because there's a few yeses in there that it sometimes got right. And so sort of critical to making this work, actually, on this data set at least, is multitask training to predict the target phonemes. If you ask it to train it to predict the source and target phonemes and output speech, it gets even better. And if you go even further and pre-train the encoder on the speech-to-text translation task, it gets even better. So now we're going all the way from 0.6 to 31 blue, which is pretty good. Although in this case, it actually underperforms, at least in terms of this metric, the cascaded system. We also did some listening tests and found sort of the same trend. It does okay, but not as well as the cascade. So finally, we've pushed things too far. These end-to-end models don't necessarily work as well. But we're going to try and make it harder, because why not? One thing we did is we just went back to that ST1 sort of larger scale training set. This time we're going from Spanish to English. Again, the ST1 is just we got people to read the speech corresponding to this translation, text translation set. So we have speech for both sides. Again, we're using synthetic targets. We use a bigger model. Now it's getting pretty big. It's about 320 million parameters. So it's harder to run on your phone without killing your battery. So we don't have a demo of this. I'm sorry. And so now that we've scaled up the training data by a factor of 7 or whatever it is, all those details kind of don't matter. Pre-training doesn't help. Multitask training is still important. It doesn't work at all without it, but it kind of doesn't matter if you try and predict the source transcript or the target transcript or both. It's all about the same. And again, it doesn't perform as well as the cascade, but the gap is narrower, so that's something. Although I guess it is also important to note that this task is slightly easier, again, in that the input speech is read speech. It's not spontaneous, unlike Fisher. So some of it's to do with scale, some of it's to do with the difficulty of the task. All right, so for our final trick, we try to go all the way and do speech-to-speech translation, maintaining the voice of the input speaker in the synthesized translated speech. Here we had to work with a subset of the ST1 data set because only a subset had people who had read the text for both sides of the corresponding translation. Everything else sort of failed QA. And sort of the important point here is it's still not it's not matched training data. The set of users who read the Spanish speech were different from the set of people who read the English speech. So we don't have like fully parallel examples. So we used a trick that worked out well for this sort of multi-speaker tacotron work that came out of our group and was presented at NeurIPS last year. And that's basically to condition the decoder that generates out the spectrogram on some speaker embedding. And we're going to compute a speaker embedding from some arbitrary reference utterance. And what we can do during training is, just to make sure things are matched, we compute a speaker embedding from the output speech that we're trying to predict. So it's sort of a little bit of a cheating setup during training, but that's all we have. So that's all we can do. And what we're going to do during inference is we're going to just compute a speaker embedding from the same speech that we're passing into the encoder of this speech-to-speech translation model. And the speaker encoder we're moving very far away from end-to-end training here. So the speaker encoder is actually pre-trained on a separate data set for speaker verification, but nevertheless it gives us a useful representation that the model can learn how to use. So I think I have an example of this too. So this is sort of the ultimate translatotron, I don't know, so far. Here's some input. Oh, what? You can, wait, let's do this. Okay, there we go. There's always a way out. All right, so the input source speech.
Larry me preguntó cómo me sentía y creo que es cuando empecé a llorar.
And the target, which we like this thing, well, the target in a different voice. This is the test set that we're not testing on the train set here.
Larry asked me how I felt, and I think that is when I started to cry.
So let's see if I can figure out these columns right. I think this is the output of the translatotron model that projects everyone to the Google Assistant voice.
Larry asked me how I felt, and then I think that's when I started crying.
She does a pretty good job. And if we try and reconstruct the source voice, this is what you get.
Larry asked you how I felt, and I think it's when I started to cry.
So this is the input speech again, just...
Larry me preguntó cómo me sentía y creo que es cuando empecé a llorar.
Larry asked you how I felt, and I think it's when I started to cry.
So is it the same voice? I don't know, but it's it's the right gender. It's not too bad. It is, yes, it is probably better than the Google Home voice. And so yeah, we also have the output of a cascade, which again is I think on this example maybe not going to do a good job at mimicking the prosody.
How I felt, and I think that's when I started to cry.
I don't remember which one that is. All right, maybe it did okay on this example. All right, so this thing kind of works. That's good. We did the same evaluation that we did before. I don't want to harp on the details too much here, but the sort of important takeaway point is, at least in terms of this lower bound blue score, it doesn't perform as well as the model. The voice transfer model doesn't perform as well as always making everyone sound like the Google Assistant. And also, we found that the speaker embedding, despite being trained on multilingual data, is somewhat sensitive to language. And so if you ask it to reconstruct the source speech, which is mismatched from training, you're giving it a speaker embedding from a Spanish speaker, which it never saw during training. It doesn't perform quite as well as if you give it a random English speaker embedding. So there's work for us to do. That's perhaps good news. Can keep paying us money. Okay. So just to summarize, yeah, these sequence-to-sequence models are pretty powerful. If with the right training data and enough sort of brute force coaxing, you can make them work even on these really hard tasks. I showed how you can make this work for speech-to-text translation. That's pretty straightforward. Multitask training helps, but it sort of becomes more and more important as the task gets more difficult. You can do speech-to-speech voice conversion just by taking a speech recognition encoder and a TTS decoder, and again, giving it lots of data. It's easy to adapt it to atypical speech if you have some training data. And yeah, finally, if we really push the limits, you can make it work for speech-to-speech translation. Okay. So just the sort of parting thoughts. I don't know. You guys be the judge, but it's not really clear to me, based on all this work, that this end-to-end, trying to build these end-to-end models is really a great idea. Obviously, it's much more difficult to collect training data. That's why we had to cheat and use a speech synthesizer. The models also seem to have different biases. At least when it's mismatched from training, Paratron seems to sort of copy the pronunciation sometimes from the input incorrectly. Translatotron might prefer cognates sometimes. And probably sort of more importantly, these giant black boxes that solve these really complicated tasks are totally opaque, right? You can't really interpret what the hell's going on. And also, at least in sort of speech translation applications, having an intermediate representation of what it thinks the source speech is actually pretty useful, both for debugging and, maybe users want to actually see that. So, I don't know. The other point I want to make is that these models are actually less powerful in some ways than cascaded systems. You only have one decode or beam search. So there's sort of less explicit representation of uncertainty and sort of multimodality in the output space. Maybe that's important. Probably more important, at least for the things that we tried, is the Tacotron decoder doesn't do beam search at all. It actually only supports greedy decoding, so it's even less powerful, which to me makes it even more surprising that it works at all, but it does. But it's probably why you need multitask training to get anything sort of coherent. Okay, and with that, that's about all I have to say. Again, this was joint work with lots and lots of other people. Here are some of them. And if Fadi wants to come up, we can do a quick demo. But he wants me to play this video. Sorry, here's Dimitri again. This is a better demo.
I'm Dmitry Kanevsky.
I am Dmitry Kanievsky.
I'm speech research scientist at Google.
I am speech research scientist at Google.
Before Google, I worked at IBM.
Before Google, I worked at IBM.
Before IBM, I worked in Institute of High Mathematics.
Before IBM, I worked in institutes of higher mathematics.
I received PhD in mathematics.
I received PhD in mathematics.
I received this at Moscow State University.
I received this at Moscow State University.
All right, works on Dimitri. Do we have time for a quick demo? All right, come see me or Fadi later, and we'll demo this thing for you. It does not work at all, really, in noisy environments. Sorry, but we can go step outside for a quick demo if you want. Oh, yeah, and I'm of course, happy to answer any questions.
Any questions for hi, it is really fascinating. Now, that does tell something about the limitations of what Dialocan calls differentiable programming and what Kaplan calls software 2.0, which is the idea that if you take high-level neural network blocks which are assumed to perform a certain function, put them together, that propagate the whole thing, then you can achieve very complex functions. So looking on the positive side of what along the evolution of your system brought improvements, what was the technical strategies we brought improvements? Was that to reduce the size of the models, or was that to change initialization, or was it to change the training recipe or the loss function? What is it that brought improvement as a contrast to
I think the results, I hope was kind of clear that multitask training is sort of the thing that made everything work. I'm not sure that I'd necessarily take this as evidence that you can't backpropagate through complicated neural network blocks to solve interesting computational tasks. It's just that these might not be the right blocks. So there's a philosophical question there which I don't know the answer to, but yeah, it definitely took tuning. Sure. Oh, that's actually a good question. Yeah. Well, so we actually didn't tune these things very, very carefully. In the speech to text translation, it's just equal weight for every task. I think just worked, it was. Yeah, exactly. In the speech to speech translation model, honestly, I'm not the one who did the tuning. That was and he's not here to answer that question. But it definitely took some tuning. All the way in the back. Yeah. I didn't talk about this, but maybe I should have. I don't think this is necessarily a good idea to use this as a front end for an ASR system. If you have sufficient training data and it's transcribed, just use that to train a better ASR model. I mean, what's useful here is that you don't have to retrain the ASR model. So, we're Google, we can control that recognizer if we want. But if Dimitri wanted to go talk to a competing speech service, Amazon Alexa or whatever, or Siri, it hopefully will work just fine. But yeah, I mean, it clearly makes a very different class of errors compared to recognition errors. I don't really know what's going to work best.
So I hope we'll see many of you in a few minutes.
And can I just ask for a round of applause for Jonathan?